Okay, so this is a set of solutions to the Markov chain problems. So let's take a look at problem number one. Here we have an airline and it has three locations. So that's going to determine the transition matrix. So remember that the froms are along the top, and the three locations here are Los Angeles, St. Louis, and Dallas. And the twos go down the side, so that's Los Angeles, St. Louis, and Dallas. And so we have a current state. The current state matrix is that there are 30 airplanes in Los Angeles, 12 in St. Louis, and 8 in Dallas, right? So this is Los Angeles, St. Louis, and Dallas. So now we have to kind of come up with our transition matrix. So during an 8-hour period, 20% of the planes in Los Angeles go to St. Louis. So that's 20% from Los Angeles to St. Louis. We have 10% of those then fly to Dallas. So coming out of St. Louis, 25% fly to Los Angeles, and 50% fly to Dallas. And then from Dallas, we have it as 12.5% fly to Los Angeles, and 50% fly to St. Louis. So the rest are making returns. So this is going to be 70% of Los Angeles stay in Los Angeles. 25% of St. Louis stays in St. Louis. And if I have 12.5 and 50%, 37.5%, I think is correct, are staying in Dallas. So if I take that P matrix and multiply that by the X null matrix, I get the result for 8 hours later, because this is an 8-hour transition, according to the problem. And you can MATLAB this, and you're going to end up with 25, 13, and 12, which means that I have 25 planes after 8 hours in LA. I have 13 planes after 8 hours in St. Louis. And I have 12 planes in Dallas. All right, so that's number one. All right, so let's take a look at problem number two. We're doing a chemistry experiment. We have a test tube that contains 10,000 molecules of a compound. That's going to tell me my initial state, because in my initial state, 20% of the molecules are gas, so that's 2,000 molecules are gas. 60% are liquid, so that's 6,000 molecules are liquid, and the last 20% are in the solid state. So my transition matrix, so we're going from gas, liquid, solid, gas, liquid, solid, right? So my transition matrix tells me if I introduce a catalyst, 20% of the molecules, oh, sorry, there we go. 40% of the gas molecules become liquid. Okay. 30% of the liquid molecules become solid. And then the 50% of the solid molecules become liquid, right? So we also have what is it? 40% of the gas molecules change to liquid. No, that's it. That's the only changes that we can have, right? So that means 60% stay gas and none go to solid. None go to gas here, and 70% stay liquid. And what do we got here? The last part is that the last 50% stay solid and none of it becomes gas. So after we introduce the catalyst, we should go P times X null, which again you can MATLAB, and you should end up with 1200, 6000, and 2800. So we're moving approximately 800 molecules ultimately from gas to solid through liquid. All right, so this is the end game here with gas, liquid, and solid. So there you go. It's number 2. All right, so in number 3, they give me the transition matrix. So my transition matrix here is 0.6, 0.2, 0.2, 0.1, 0.7, 0.2, 0.1, 0.1, 0.8, right? X null, so the initial state is 10%, 10%, and 80%. So I want to know what is x3. So remember, x3 is p cubed, right? So that's going to be like p times p times p cubed times x null, which ends me up with the matrix that once you MATLAB that, and you can just use the caret in MATLAB, you need like p caret 3 star x null would get it to you. Is 0.1875, 0.2477, and 0.5648. That's what you get when you MATLAB it. All right, so that would be the third state away from the initial state. So there you go. Okay, so looking at problem number 4. Let's look at problem number 4. What do we got here? Students in a gym class have 2 choices. So this is a pretty simple one. It's only going to be a 2x2 matrix. The 2 choices here are swimming and basketball. Oops. Swimming and basketball. Wow, having trouble with letters tonight. There we go. Swimming and basketball. 30% of the students who swam one day will swim the next, so 30% stay there. And 60% of the students who play basketball one day will play basketball the next. So this has to be 0.7, and that has to be 0.4. The initial state is that you have 100 swimmers and 150 basketball players. So we want to take p to the 4th, right? Because we want the 4th day times x null, which lands me at a kind of a weird answer here. It gives me this like 90.9100 and 159.0900. So we really can't deal with these as people because people are discrete. So we're going to round that to 91 swimmers and 150. On the should be 159 basketball players. All right, so there you have it. All right, so let's take a look at number 5 here. 5 gives me the transition matrix. It says P is 0.22, 0.20, 0.65, 0.62, 0.60, 0.15, 0.16, 0.20, 0.20. All right, so the way that we find the steady state matrix is we have to take the transition matrix to a high enough power. So I used like p to the 10th. And then I have to pick some initial matrix. And this can be completely arbitrary. I used 0.3, 0.3, 0.4. You could literally use 1, 0, 0. It doesn't matter. Just so long as that the matrix starts or adds up to 1 going down. If I do that to the 10th power, I get 0.2906, 0.5210, 0.1884. Now, I need to verify that this is the steady state, so what I do is I take the next power. And if I take the next power and I get the same thing, that means that my matrix is now stuck in that state. So this is my steady state. So X bar will be this 0.2906, 0.5210, 0.1884. And that's my steady state. So that's number 5. Okay. This is like one of those like no kidding moments. Problem number 6. I actually wrote this problem a year ago, and I'm bumping into it like headlong, like, oh my gosh, this is ripped from the headlines here. All right, so we have a situation where we have a population of 200,000 people, and 40,000 of them are infected with a virus. After a person becomes infected and then recovers, the person is immune, so they cannot become affected again. Of the people who are infected, 5% will die each year, and the others will recover. Of the people who have never been infected, 25% will become infected each year. And how many people will be infected in 4 years? So we actually have 4 states in here. We have never been infected, currently infected, recovered, and unfortunately dead. Never been infected, recovered, and dead. We have that 75% of the never been infected will remain that way, and the other 25% will become infected. Of the infected, 95% will recover and 5% will die. Not a little bit more bleak than our current situation with the coronavirus, but it's actually a pretty close model. Because I think corona is around 97 and 3. Of those recovered, 100% will stay recovered. And for better or for worse, of those who died, 100% will remain dead. Okay, so the current or original state is to take the 200,000 population and say that 40,000 of them are in the infected state and 160,000 are in the never have been infected state. And the question is if I go 4 years from now, where would I be, given that the cycle of infection here is typified as a year? So at the end of that period, I would be 50,625, 16,875, 125,875, and 66,225. So the question is how many people would be infected in year 4? The answer there would be that the state for year 4 would have 16,875 currently infected. All right, so sorry if that's a little bit too on the nose, but it is a great explanation and use for Markov chains that's kind of ripped from our current headlines. So there you go. Thank you.